Dan Freed, Director of the CMSA. Pleasure to welcome you here for this summer school. Word about the CMSA. It's a center here at Harvard. We voted to the two-way interaction of mathematics with sciences, with physics, with computer science, with economics, biology, and so on. So I encourage you, there are some newsletters lying around. Encourage you to take a look, see what we do here. There's also a short film you can find on our website. And with that, I'll give it over to John.
Thank you so much. Yeah, thank you all for coming. We're really excited for the summer school. Just want to kind of make a few quick reminders and then turn it over to Lara. First of all, I just want to say that thank you all for being so flexible as we arrange this and as things change weekly. And I'm going to throw one more change. We're going to change the schedule a little bit with just some of the exercise sessions swapping with some of the lectures. And we'll make a more concrete announcement at some point, but there have been some swaps in the order of the speakers, and to make it kind of work reasonably, we're going to also make changes in the exercise sessions. Also, I just wanted to make sure to remind people to fill out, who are getting reimbursed travel, to fill out those forms ASAP, and you can ask Maureen or Allison upstairs for help if you need any help. We want to make sure that we reimburse those funds as fast as possible. Also, if you're going to speak at the lightning talk, please make sure we have your slides so we can have that arranged by the end of the day. And yeah, thanks so much for coming. And also, we'll have lunch provided in the common room upstairs where the coffee was. And during both the coffee breaks, you can have coffee and tea from the machines. And in the afternoon, we'll also have some snacks. There's a few coffee shops nearby if you want a snack in the morning that you can run to within that time period. With that, I'll turn it over to Lara. Thanks so much.
Thank you so much, John and Matteo, for the invitation and for making it happen. As I already mentioned earlier, this is the first event where I would like to thank the organizers that, besides all the challenges, they managed to get us all here together. So I'm pleased to be here, talk about some of my favorite topics in math. I'm a mathematician. So we're gonna have quite a long schedule today, talking about positive Grassmannian and cluster algebras. Don't be scared, this is the schedule for all my lectures. One is what I'm gonna try to cover today, and 2 and 3 are done for the other 2 lectures. So today we're gonna dive into total positivity, talking a bit about totally positive matrices, and then slowly getting towards the Grassmannian and the totally positive, totally non-negative Grassmannian. And then tomorrow we're gonna take it over to cluster algebras. And later I would like to add some things on partial flag varieties, as those are the cluster structures or the mathematical spaces relating to the physics. So let's get started. I want to invite you to ask questions throughout the lectures, whatever comes up, any doubts you might have. I also want to invite discussion in the room so that we're not only in this me talking and you listening dynamic. So feel free to interrupt me whenever. So let's get started with totally positive matrices. We're going to start with linear algebra. It's a very elementary problem. So if I have first setting up a bit of notation, fixing n will always be a positive integer. And this notation with the brackets is what I use for the set 1 to n. And then n choose k, the symbol is denotes the set of k element subsets of 1 to n. And if I now fix a matrix, we're going to mostly be working over the real numbers, so we can talk about positivity. N by n matrix with real entries. Then my notation for minors of this matrix is the following: delta ij. So I choose I and j to be subsets of 1 to n of the same cardinality k. And the delta ij of m simply denotes the determinant of the submatrix with indices in the corresponding index sets. And if now I evaluate all possible minors of m, all sizes of minors, and all of them turn out to be real, well, they are always real now, positive or non-negative, then the matrix M is called totally positive or totally non-negative. Okay, so that's like the basic definition. So I have a very small example to illustrate this. The first non-trivial example. So if I have my matrix 2 by 2, n is 2, then I have 5 minors to evaluate. Every entry is a minor. So all of my entries have to be positive or non-negative, and the determinant itself is also minor, so that also has to be positive or non-negative. And well, then the determinant can be expressed in terms of the entries of the matrix. So we have they're not independent, all the minors. And this is the first observation you can make, is that in order to check if my matrix is totally positive or not, I don't actually have to compute all the minors, but just 4 out of 5 in this case. And that number becomes, that difference becomes more significant when the matrix grows. So here are 2 questions that are generally of interest. The first one, well, if we want to know if a matrix is totally positive or not, we would like to do that as efficient as possible. And the second one, so the first one is interesting for applications. And the second one is more interesting for mathematicians. I've always wanted to understand the structure and the pattern behind. So we would like to characterize totally positive matrices. Yeah. And you might wonder, sometimes we're going to have some typos in my slides because I translated them from Spanish. So if you find some, please let me know to fix that before sharing. Okay, so is that clear until now? Great. So then I'm gonna be focusing more on the second part of the second question to get into like the more interesting structure and the combinatorics behind totally positive matrices. So in order to do that, I'm going to talk a bit about planar networks and how to associate matrices to planar networks. A planar network, for me, of order n, is a planar directed cycle-free graph. It has 2n vertices, which are n sources and n sinks. And then the weighted part of it is assigning scalar weights to the edges. So here's an example. I have these 2n, I should rather say 2n special vertices that are on the left and on the right here. So I didn't count the other vertices. They are the number of vertices, the internal vertices of my graph. So that's the thing to fix. There's no restriction on how many vertices are in the interior of the graph. This 2n just refers to the left, which I'll be thinking of as the sources, and the right, which I'll be thinking of as the sinks. So in this graph, I would think, I didn't draw the orientation, but the orientation would always go from left to right. Okay. And then I'm assigning scalar weights, so real numbers to all the edges. I have lots of edges labeled 1 here. It's just a choice. And then the colored edges are the ones that carry labels A through F, A through, well, wherever. And yeah, I assume them to be real numbers. Okay. And to every such matrix, to every such network, I can associate a weight matrix. And it's going to be an n by n matrix. So the order n of my planar network determines the size of the matrix. And the ijth entry is the sum of all weights of paths from I to j. So I've labeled my n vertices on the left, 1 to n, and on the right as well, 1 to n. And if I now choose I and j, meaning I choose I somewhere on the left side, j somewhere on the right side, then I would consider all paths through my graph from left to right. And the sum of all the weights of the paths, all the weights of all the paths is what determines the entry of the matrix. Okay? Yes?
And are the weights real numbers?
Yes, yeah. They're the numbers. So here's the first exercise that also appears on the exercise sheet to complete the weight matrix of this graph. And I've done 3 examples for you just to illustrate what the weight of a path is. So for example, the one entry of my matrix means I start at 1 and I end at 1. And there's only one possible path going through this edge D and through the other edges labeled by 1. The weight of the path is the product of all the weights along the edges. So D is the only interesting weight of an edge here, and that's the weight, the entry of my weight matrix. And then if I choose to go from 1 to 2, so I want it to the 1, 2 entry, well, I have to pass through the weight, the edge labeled H, so I get the D times H, okay? There, I didn't put the definition of the weight matrix on the exercise sheet, so ask now, because otherwise you might not be able to solve. Yes?
On the slide it says the sum of the weights. Would it be the product as you?
Yeah, yes, very good, thank you. Totally imprecise here. So the weight of one path is the product of the weights along the edges. And if I have two paths, it would be the sums of the weights of the paths. Yeah. No, thank you so much for pointing it out. Everything else is clear? Great. Okay, so then, yes, if the rest of the talk gets boring, you have a first exercise. Take a quick picture of the, well, I think it's on the website already, so you can start playing with that. Okay, great. So here's one of, I don't know, like one of the nicest results in algebraic combinatorics is Lindström's lemma, or one of my favorites, not to be judging other results. So if I have a planar network of order n, and M be its weight matrix, then I can also compute every minor of my matrix, of this weight matrix, using the graph. And the way to do it is the following. So if I have a minor delta ij of M, so I and j are now index sets of same size, then the value of this minor is the sum of weights of collections of vertex disjoint paths connecting connecting vertices in the source set to the sink set. So I is what I think of as my source set. J is what I think of as my, and put the picture, sink set. And for ij, I'm not only now, for the entries, I just computed all possible paths and took their weights and the sum. And now I'm going to take collections of paths, connecting all the vertices in I with all the vertices in j. And the only condition is that they're vertex disjoint. So the paths that I consider cannot be crossing. And if I do that, then this will give me the value of the minor. Okay, so I did one example of going from 2,3 to 2,3. And let's maybe check FE, which is the easiest one. So FE corresponds to a collection of two paths. I have two indices in each set. So I want to go from 2 to 3 and from 3 to 3. I cannot go from 2 to 3 and 3 to 2 because that would always mean the paths are crossing, which is not allowed. So just go from 2 to 2 straight and from 3 to 3 straight, which corresponds to E and F. So this is a collection of paths, and the weight of the collection of paths is the product of the weights of the paths. Okay, so F is the path 3 to 3, and E is the weight of the path 2 to 2. And then there's other more complex combinations, and we could exercise also first to check what are the paths corresponding to these weights, and then is this an exercise? No, I didn't mention it, but you might as well compute more minors of this matrix in the exercise. Okay. Okay, I saw some confused faces when I first read the result. Still confused? Any questions or? Okay. Great. Otherwise, also in exercises, feel free to ask more questions about. Okay, great. So my example here looks a bit particular. It's a very symmetric graph, and it is an example of a graph that is really important to this theory of totally positivity in matrices. And it's the example where n equals 3 on this graph. So I take this example graph on the slide before, and I just extend it until I have a network with n sources and n things in the same structure. On the left, I have these edges diagonally going down, middle edges straight, and on the right, edges going up. The colored edges is what I would call essential edges in this network. And those are the ones where I'll be more interested in putting weights on. All the others you already saw, I just labeled them as 1. And the reason for that is this following result. It's you can find it as a theorem in a paper of Fomin and Selevinsky called think, totally positive matrices, but the title is longer, and it's based on a previous result by Whitney, and it totally characterizes totally positive matrices of size n by n. So here's the result. We have a bijection between the set of essentially positive weightenings of G0. So G0 is this weight up here, this graph up here. And a weighting is called essential if at least one of the colored edges has a non-zero weight. And at least one of the essential edges, and all the others have weight 1. Okay, so all the black edges would have weight 1, meaning I can essentially ignore them when computing the weights of any paths. And then at least one of the essential edges, I want them to have a non-zero weight. And then there's a bijection between the essential positive weighting. So I want this at least one non-zero weighting to be a positive real number, and totally positive n by n matrices. Okay. So the proof is actually very interesting because it really uses linear algebra results about LDU decomposition in matrices. So what you see in this graph, if you would take a subgraph here, maybe just keep one of the colored edges, ignore all the others, that would correspond to an elementary upper or lower triangular or diagonal matrix, depending on the color of your edge that you choose. So what we have here is a graphic representation of an LDU decomposition of a matrix. So if you take your matrix, you decompose it into lower triangular, diagonal, upper triangular matrices, and go down until these matrices are essential or elementary, then you will be able to read off the graph from your decomposition, or vice versa. And that's the proof of this. Okay. Any questions?
Do you want all of the middle edges to be positive?
So I want, for this essential weighting, I want at least one of them to be positive. And I mean, I don't allow negative numbers. So if I want an essential weighting, then all the colored edges have to be, can it be 1? What is it called? It's non-zero for at least 1, and then in the result I need it to be positive. Yeah.
If you do have 0 edges, do you maybe get totally non-negative matrices sometimes?
Yes. Okay. Oh, yes. Thank you for mentioning that. So actually, yeah, this result is the totally positive case, which is the LDU decomposition. The proof is the LDU decomposition. You can extend it to totally non-negative, where the proof gets a bit more complicated. We get some limit or boundary conditions, and yes, that's when we allow 0 weights. Yes, thank you. Okay. So totally positive matrices, all edges have positive weights, can be 0, can be 1, sorry. And yes. Okay, good. So I think, yes, this was it on totally positive matrices. And we're now going to move on to Grassmannians and see what kind of results or generalization of these kind of results carry over. Okay. So for the Grassmannian, in case you haven't seen it, is the following set. Its elements are vector spaces of a fixed dimension D in a vector space, in an ambient vector space k to the n. So for us, mostly k will be the real numbers. And we can represent its elements as matrices by 3 simple steps. The first one, we want to fix a basis for the ambient vector space, k to the n. In the second step, when we have an element of the Grassmannian, we're going to fix a basis for that vector space. It's a vector space, so we fix a basis. And then in the third step, we express all the basis elements of my vector space V in the basis I chose for the ambient space, and the coefficient of this decomposition is what we write into a matrix. So as my vector space V is of dimension D, and my ambient vector space is of dimension n, I get an n times D matrix. Okay. And now this matrix I associate to a vector space is not unique. It depends on two choices I made, the basis of the ambient space and the basis of my vector space. And so this matrix MV determines the vector space, but there's many matrices I can associate to one. And they're all related by base change, and that I will assume point 1 is fixed once and for all. So I only depend on base change for my vector space V. That gives me a GLD action on relating all these different matrices representing the same vector space. Okay. Okay. So in order to parameterize the Grassmannian, we usually rely on Plücker coordinates or minors of these matrices. And the minors that we're interested in are the maximal minors of the matrix, which we started with a vector space of dimension D, so at least one of them is going to be non-zero, and we get some valuable information of the vector space out of considering these minors, and they're called Plücker coordinates. So if let's check one thing about Plücker coordinates. If we now have one vector space in the Grassmannian and we fixed one basis for it, and we got a matrix MV out of it, and then we take another collection, another basis for the same vector space, and it gives us another matrix. So there's, as mentioned, a matrix in GLD that relates the two matrices MV and MV prime. And these minors, the Plücker coordinates, they change, but they all change in the same way. And that is with common rescaling. That is the determinant of my base change matrix A. Okay, so on the left, I have the minor, the I minor of MV prime. On the right, I have the rescaling of the minor, the I minor of MV. Okay, and that is the observation we need to convince ourselves that the following theorem is true. If we take a vector space and map it to its collection of Plücker coordinates, running through all D element subsets of 1 through n, calculating all these minors, that gives us an embedding of the Grassmannian into a projective space. No, what we just verified is that this embedding is well defined. And so the Grassmannian in this way obtains the structure of a projective right. Okay. Okay. Questions or comments? Did anyone here not see the Grassmannian or the Plücker coordinates before? Great, perfect, okay. I'm boring everyone. So I hope you're done with the exercises, huh? At least the ones on the network, the first one. Okay, so this slide is then rather to set up my notation because I'm going to need Plücker relations as well. So I defined my Plücker coordinates here corresponding to an index set, but I might as well do it corresponding to a tuple of indices where I choose the indices in a fixed order. And if I do that, meaning I change the order of my indices here, I would also rearrange the submatrix that I'm computing the minor of. So the relation between reordering, like a tuple I1 to ID, and the reordered version of that tuple is a sign that depends on the number of reflections in the permutation that I used. Great. So with that, I can define the Plücker relations for tuples or like pairs of index sets. And here I'm choosing one index set that is missing an entry to get to a D element set, and one that has one too many. So my Plücker relation corresponding to this choice of I and J will start with the Plücker relation where I choose the first element of my set J and put it into the first tuple. And then I run through all possible combinations where I always omit one index from the set J and I add that one into the index set I. And I needed the sign because I don't want to take care of the signs in my relation. So I'm just gonna, outsource that for later. Okay, so that's a Plücker relation, and I take all of these relations together, define an idea in the polynomial ring where now the Plückers are placeholders for my variables, and the homogeneous coordinate ring of the Grassmannian in this Plücker embedding that we just saw on the slide before is the quotient of this polynomial ring in Plücker coordinates by the ideal generated by Plücker relations. Okay, and this part of the proof, I could have added this to the proof on the slide before. This part of the proof is the one that requires a bit more work, but it's also a direct proof of just checking both containments that the Grassmannian satisfies all these equations, and that the variety cut out by these equations is actually the Grassmannian. Okay. So here's another exercise. We'll need that for the next talk, so you might as well do that today. If I'm in the very gentle case where D is 2, all my Plücker coordinates, the non-trivial Plücker coordinates all take this form. There's only 3 terms in a Plücker relation, and yeah, they depend on 4 indices between 1 and n. Okay. Good. Questions or comments? Okay. Great. Okay, so tomorrow I'm gonna pick up at least this 3-term Plücker relation. Great. Okay, so let's get into more structure, or a more interesting structure of the Grassmannian, and that is a stratification that we can define using matroids. So here's the definition of what a matroid is. It's a pair, E and B. So E is a finite set. It's going to be 1 to n for us most of the time. Actually, I think all of the time. And B is a non-empty subset, a set of collections of subsets of E, and those will be called bases. And they satisfy the property. It's called the base exchange property, the one I'm giving you here. So when I take two of these subsets, B1 and B2, then and one element in B1 that does not belong to B2, then taking out this element of B1, I can find another element in B2, add it into my set, and what I've created will be again a basis. So I don't require that B1 and B2 are related by just exchanging one element. I just require that when I take an element out of B1, put in another element of B2, that again belongs to my set of bases. Okay. And to make it a bit more precise, you can totally think about only matrices. So in this case, elements of the Grassmannian, if you want to think about a matroid. And the way to do it is the following. So we take a point in the Grassmannian, and from now on, I'm going to be a bit lax about having actually a point in the Grassmannian a vector space or a matrix. Okay, every now and then I'll write a matrix in the Grassmannian, and what I mean is it represents an element in the Grassmannian. So if I take a point in the Grassmannian and I compute all its Plücker coordinates, so I take a matrix representation, compute the maximal minors, then the collection of index sets where the minor is non-zero, that determines the matroid. Okay, so I have my, what did I say, n times d matrix, or d times n times d, right? N times d matrix, I compute all the maximal minors of this matrix, all the d by d determinants of submatrices. And whenever it's non-zero, I put in my collection of index sets. And all of those determine a matroid. Okay? And this matrix is called realizable over K. There's a big investigation going on about non-realizable matroids, or depending on the base field, if a matroid is realizable or not. But for us, we're going to be interested in those matroids that we get out of the Grassmannian. So automatically, they're going to be realizable in the sense that there is a matrix that realizes it. Okay. And okay, here's an example. Oh, okay. So I think I'm not very good. I think I prefer this convention for my matrices, having them d by n. Okay, if they're transposed at some point, yeah, help me to fix that convention throughout the rest of the talk. So this is an element of the Grassmannian in the sense that it's a rank 2 2x4 matrix. I can compute all its minors. Some of them are non-zero, one is 0. So in order to determine the matrix, this should also be M. What is my matroid? Well, my set E will always be 1 to N, so that's just 1 to 4. And then in this set of bases, I'll just remember all the index sets of Plücker coordinates that are non-zero. So here I have all the 2-element subsets of 1 to 4 that correspond to non-zero Plücker coordinates. So 3, 4 is the only one I omit because it was. Okay. Right. Perfect. So this gives me a stratification, called matroid stratification or Gelfand-Serganova stratification of the Grassmannian, where strata correspond to subsets of the Grassmannian, where I collect all the elements of the Grassmannian that give me the same matroid. Okay, you can imagine, I mean, I have many matrices that have this matroid associated with them, and those would all define one stratum in the stratification. So this is great. We kind of translated, we have like a nice combinatorial decomposition of the Grassmannian, but at the same time, the strata of this decomposition are extremely complicated. There are some results showing that essentially the topology of the strata can be as complicated as that of any projective variety. So we have a nice decomposition, but it doesn't really help us too much to understand the Grassmannian because we decomposed into still very complicated things. Okay, and we're going to see for the rest of today, hopefully, or otherwise tomorrow, how the situation becomes much nicer if we focus on a special subset of the Grassmannian, namely the totally positive Grassmannian. Any questions on this slide? Comments, concerns? Some confused faces.
Is each component of this strata like actually a subvariety, or is it just like a set theoretic decomposition?
Oh, that's a good question.
Determined by the vanishing of a Plücker coordinate, so
Yeah.
because that's a
Okay,
polynomial
yeah,
relation.
yeah.
I was thinking if
But when you talk
Just-
about the topology of this strata, like what are you referring to?
like, oh, well, it's like the algebraic topology of those varieties.
As like a complex or okay.
Yeah.
Yeah. Like the analytic topology.
So I'll modify it. I said the closure is a proper variety because the
Yeah.
closure is defined by the vanishing of relations.
yeah.
The actual cell is like the vanishing mod, not the vanishing of other relations of other Plückers.
Yeah, so you
Yeah.
have Schubert cells appearing here. Yeah. Those are the more better understood ones. Yeah. And then their closures would be Schubert varieties. Mhm. Okay. Good. So great. I think then now we're finally getting to the totally positive Grassmannian. So here's the definition. Now, whenever I talk about the Grassmannian, I'm thinking about it over the real numbers. And the totally positive part of the Grassmannian is the subset of all elements where all Plücker coordinates evaluate positively. The totally non-negative one is the subset where all Plücker coordinates evaluate totally non-negatively. So the example we had on the slide before, we already checked. It's an element in the totally non-negative Grassmannian, but one of the Plücker coordinates was 0, so it does not belong to the totally positive Grassmannian. And here's a very nice result of Postnikov that takes this decomposition, the matrix decomposition of the Grassmannian, and studies only its effects on the totally positive Grassmannian, totally non-negative Grassmannian, sorry. So here I pick M, a subset of collections, of D-element collections of N. And I denote by Sm the set of elements in the Grassmannian where a Plücke coordinate is positive if and only if its index set belongs to M. So here, by this, you know that M must have been a matroid for this set to be non-empty. Then I can consider the decomposition of the totally non-negative Grassmannian, and the result that Postnikov proved is that in this case this is actually a cell decomposition. It's a regular CW decomposition, and in particular all of these cells are open balls, so they have a much nicer topology. We're actually able in this case to decompose into simple objects. Okay. So whereas if I leave out this greater or equal on the left, this decomposition becomes quite complicated. But if I only consider the intersection with the totally non-negative Grassmannian, all the elements in the decomposition, or the parts of the decomposition, become open balls. And if I happen to find one of these matroids M, so that Sm is non-zero, then this M is called a positroid, and Sm is called a positroid set. Okay. Great. So this is maybe mathematically a good reason to study the totally non-negative Grassmannian, because it has way richer combinatorial structure, or way nicer combinatorial structure than the whole Grassmannian itself. Okay. Great. So let's see then what else we can say about these cells Sm. For the rest of today, I'm going to try to convince you that they are combinatorially very nice, in the sense that we can associate networks or something similar to networks to them and understand their elements from a combinatory point of view. Okay. Yes. Okay, so in order to do that, I will introduce you to Plabic graphs. Plabic refers to planar and bicolor, just picking up the play and the bic. So this is a graph that is planar, bicolored, embedded in a disk, with vertices on the boundary that I label 1 to n. So I want them to be n of them, and I want this graph to satisfy the following conditions. The first one, every boundary vertex is only incident to a single edge. The second, if I have an internal vertex, I'm going to color it black or white, hence the bicolored. The boundary vertices don't have colors. And all vertices are connected to the boundary by some path, so I don't have like floating isolated components in the interior of the disk. And then also in the interior, I don't allow leaves. Leaves are vertices incident to a single edge. So here's an example of a Plabic graph. I have my five boundary vertices labeled 1 to 5. And then I have a bicolored connected graph in the inside. I can have, there's no condition saying that I can have two components of the graph that are both connected to the boundary. So I could have another component of the graph here that internally does not connect to this one. That's allowed. It's just not allowed to have like a floating component that is not connected neither to the to the boundary through any. Okay. So given a Plabic graph, I want to study orientations of it, and I'm interested in special orientations that are called perfect orientations that satisfy two crucial conditions regarding the orientation along the internal edges, vertices, sorry. So if I have an internal vertex that is black, I require that there is a unique outgoing arrow from this vertex. And if it's white, I require that there's a unique incoming arrow. So down here is an example of a perfect orientation, and you can check, for example, this white vertex has a unique incoming edge, all the others are outgoing. This black one has a unique outgoing edge, the others are incoming, and so on. And so one more piece of notation to relate the Plavi graph to a Grassmannian. You already see the index n coming up, so it's probably going to be some Grassmannian dn we're going to associate to. And how to decide which Grassmannian this will be, we're going to focus on the number of black versus white vertices in the interior. So if my graph is going to be is called of type kn, if I have n boundary vertices, and then the difference between k and n minus k corresponds to this sum on the right, where I run through all the internal vertices of my graph. I have one number here that's the degree of the vertex minus 2, so I ignore degree 2 vertices. And then I multiply this number by 1 if my vertex was black, or it gets the sign -1 if it was white. Okay, so one exercise that is not on the exercise sheets, but that maybe if you can take a picture of the graph, you can do it now, is figure out what's the type of this graph. Anyone else? Everyone done with taking pictures? I want to take pictures? Great. Okay, so then how do I get from a perfect orientation of a Plavi graph to a matroid or a cell in my cell decomposition? Well, this is one way to do it. There's several ways. This is the one that is the most compact and easy to present in a talk of 1 hour. But in the paper, there's a paper on the archive by Postnikov where he presents all this theory, and there's several different ways of how to get the matroid I'm going to define now. So for that, I'm going to focus in. So I fix my Plavi graph, and I fix a perfect orientation. In particular now, if I consider only the boundary vertices, there's going to be some boundary vertices that are sources and others that are sinks. They're all of degree 1, so there's no other choice. And I'm going to remember all the sources of this orientation. So IO is my source set of a perfect orientation O. There's a fixed Plavi graph in the background here. And one exercise on the sheet is to show that if I fix my Plavi graph G and it is of type Kn, so I did my exercise of counting black and white vertices and comparing them, then the cardinality is K, is always the same cardinality. So every source set of a perfect orientation has the same cardinality. And now you can guess what is the matroid. So the matroid I associate to a Plavi graph G is the collection of all source sets of all perfect orientations. So I fix my Plavi graph, I compute a perfect orientation, I compute its source set, and then I compute and I do the same for all possible perfect orientations. This sounds quite bad in the beginning. If I give you this problem, you're like, okay, but how do I know how many perfect orientations? When am I done? There's some nice tricks you can do if you have one perfect orientation to get another one, and that is fixing one single path from boundary to boundary and flipping the orientation of that path. That would automatically give you another perfect orientation. Okay, that's another exercise you can think about and check. So at least there's a combinatorial method of how to get there. Yes.
That correspond to some combinatorial operation on the positride, like flipping the orientation along the path.
Oh, I mean, it just exchanges. Okay, if I fix a path.
Some species exchange.
Yeah. I don't know the precise answer, but I feel like if we think about it, we can figure it out. Yeah.
Yes, we need exchange of one source with the C.
Yeah,
And so then you talk about the matrix representative changes they represent.
yeah, so
I mean,
okay,
bigger.
let's see. I mean, this one is my, this would correspond to my basis 1, 2. If I take my path 2 to 3,
Yeah, because it looks like you're throwing out an element of.
Yeah.
And then throwing something.
I'm replacing the source for the sink. So that's the next basis. But so one perfect orientation is just one basis in the metroid. So yeah, there's yes. Very simple operation. Okay. Good. Okay. Great. Yeah. So this is how we can associate. I think I'm ready to prove the result. So we get for every Plavik graph. Oh no, I think I have one more slide. Yeah, for every Plavik graph, we run through all perfect orientations. We get a matroid. Okay, so that's the summary of the last few slides. And there's more to it. I think I could already state a result here, like okay, great. So we got to the point where we made Plavik graphs are associated to matroids, so they give us information in this matroid stratification of the Grassmannian, but we're interested in the positive Grassmannian. So we want to see how to get actually to the positive Grassmannian. And there's a result, or there's a way to do that. That's along the lines of the Lindström lemma. So what I'm going to present now is the generalization of Lindström lemma, or the Fomin-Zadowiński-Whitney theorem, to get from Plavik graph to a point in the totally positive Grassmannian or the whole cell. And for that, we're going to do a similar procedure as before. So before we had these planar networks, we associated weight to the edges, and we computed a weight matrix for that. We're going to do the same here. So we take our Plavik graph, we fix it to be of type Kn, and then we associate weights, positive real numbers, to, in this case, it's faces. There's a way to associate weights to the edges. I prefer the faces. It will become clear why. The calculating the map is a bit more complicated when working with faces, but especially having in the back of my mind that I want to get to cluster algebras, this is really the right thing to do. So if I assign weights to faces, f of g is the set of faces of my graph. I require that the product of all my weights is equal to 1. Okay, one extra condition here. So this combination now of a Plavik graph G with a perfect orientation O and assignment of weights to faces with this condition is called a Plavik network. And to a Plavik network, I will associate a matrix. And the idea is similar. So I choose an index I and an index j, I in my source set, j in my sink set. So the matrix is not going to be square, right? Already now we see that, okay, we said source set is cardinality k, so we're going to get a k by n matrix. And then the ijth entry is corresponding to paths going from I to j, from boundary to boundary. I associate a weight to the path. It's going to be the product of all the weights of faces to its left. I'm going to have an example. Let me just put it up already. So I consider my path, for example, 1 to 3, this one. And the weight of this path would be y1 times y2, weights of faces to its left with respect to the orientation of the path. I have to take into account like this sign here that that's called the winding number, that counts the number of 360 turns my path could take, because I might have oriented cycles. So I could like spin around certain faces and they would be on the left and they would come up in my weights and so on. If you like, you can ignore that technical detail. It will not appear in the example, certainly. And then again, I take the sum of all these paths. Okay, so my ijth entry of the matrix that I associate is corresponding to paths from I to j, taking the sum of their weights. Right? I'm gonna leave this to like a second to digest. Yeah, so here's this. Okay, I did the example 1-4. It also appears on the exercise sheet. So from 1 to 4, I have apparently 2 paths. That's what I claim. So let's see if I did the computation correct. I start at 1, I want to get to 4. So first I walk into this white vertex. Then I turn like totally left here, go down to the black one, down to white, black, white. So that gives me this y1, y2, y3. So the 3 faces to the left. And then the other is going around this 6th face on the other side, which would also include it in the weight. Okay. Great. So another exercise is completing this matrix. And now, yes, okay, I'm ready to state the result. So what did I do here? And let's just quickly go back. Plavik network was Plavik graph with perfect orientation and weights associated to faces. And I associate this matrix Mij. So I have a map that takes as input G, O, and Y and gives me a K times N matrix. G was of type Kn. And this is called the boundary measurement map. And it goes from Plavik networks of type Kn. And the theorem Postnikov proves is that it goes into the totally non-negative Grassmannian. And if I now restrict myself to Plavik networks that have the same underlying Plavik graph, so up here I fix G and I run through all the O's and Y's, then this map only goes from the positive orthant of dimension number of faces -1 because I had this condition that the product of all the weights of the faces is equal to 1. So I go from the positive orthant number of faces -1 into the totally non-negative Grassmannian. And the theorem is that the image of this restricted map is the positroid cell, where the positroid, so the matroid realized in the positive Grassmannian, is the one corresponding to the graph. Okay. I'm going to wait a second. You can digest this, come up with questions, doubts. You can also complain that this sounds super technical and you're completely lost. I should have put more interesting examples. Yes.
I still have the question, when can I tell that I found all the perfect orientations in G?
That's a tricky one. That's a tricky question. So with this, so this procedure of the perfect orientations is not very satisfying because you don't know when you're done. I mean, now with this result, you could be a bit more. Yeah, so I mean, now what you can do is you can compute the matrix associated to one perfect orientation. Like you do this procedure and then you compute the matroid of that matrix, right? Because after this result, we know that all the elements here have the same matroid. So if you have one matrix in the image, you can compute the matroid. But that's of course not the proof of the theorem. Yeah, there's other interpretations of how to get to the matroid, working with perfect matchings, like making your Plavik graph. Oh yeah, actually, I still want to maybe get there today. Let's see, 5 minutes is okay. There's operations you can do on a Plavik graph, and then you can compute perfect matchings if your graph is bipartite, and that will also give you a procedure to get to this matroid. But I don't expect you to understand this from just what I said now. It's rather, if you're very interested in it, I would recommend going to this paper by Postnikov, or also lecture notes by Lauren Williams that are, I have them in the reference. I'll show you the reference in a second, that have more details. It's like 1 page. It's not very complex, but it's something to get into. Yeah. First I considered talking about the perfect matchings, but then this one was the one that fits more condensed into a 1-hour talk. Other questions? Okay, so then let's check, it goes into the direction of your question. Let's check a bit more combinatorics of Plavic graphs and how they are related. So there's this very nice operations on Plavic graphs that have powerful interpretations on the Grassmannian and on the cells. So let me give you the combinatorics first. These are 3 operations called moves, the first 3, and the last one that is called reduction. So for the first one, the square move, this is a local picture of my Plavic graph. And before you perform the square move, it's very important that you actually have this picture. So if one of your vertices here is not trivalent, you cannot perform this move, right? It has to look exactly like this. So you find a square that is bipartite, all the vertices trivalent, and then you can swap the colors. Okay. Now, if you find a square but it's not trivalent, the moves 2 and 3 might help you to become trivalent. So move 3 is quite simple. If I have a 2-valent vertex in the interior, I can ignore it, but I can also insert it whenever it's convenient for me. And the M2 move is merging vertices of the same color. Okay, so let's say if you have, and I can also unmerge them. So if I have one vertex of valency 5, I can put it apart into 2 vertices, one of valency 3 and the other one of valency 4. So I connect them with one edge, so I have 2 outgoing on one and 3 outgoing on the other. So I think one exercise on the sheet is checking that you can use moves 2 and 3 to make a Plavic graph or trivalent or bipartite. Not both at the same time, but those operations will make it possible to put these extra conditions on your Plavic graph. And then the last move here is called the reduction because I cannot reverse it. So whenever I have 2 vertices of opposite color and they're connected by 2 edges, I can completely eliminate this configuration from the graph. Okay, and I only do that in one direction. Okay, so a bit more terminology. So if I have 2 Plavic graphs and I can get one from the other using only these moves, 1, 2, 3, they're called move equivalent. If I can apply this last operation on my Plavic graph, R, then it's called reducible. And a Plavic graph is called reduced if there are no reducible Plavic graphs in its move equivalence class. Meaning I take my graph, I do all the moves 1 to 3 in all possible directions, and I will never encounter this configuration of 2 opposite colored vertices connected by 2 edges. Then it's reduced, okay? Again, this is a definition, yes, but it's very unsatisfying because like, given this definition, how would you know when your Plavic graph is reduced? And that was like there was lots of research in this direction of finding a better characterization. I think it has succeeded, but right now I don't have the results or like an easy to state result of how reduced Plavic graphs are characterized. But we do have a better understanding of them by now.
You compute its canonical form and see if it factors.
If that's more easy to you, you do that. Maybe we'll learn it from Simon how to do. Or in your lectures?
No.
No. Good. Okay. So let me see. There was one. Yeah. Maybe let me stop with this exercise. Okay. It's the one I already mentioned. So using these moves 1 to 3, Plavic graph can be transformed into a trivalent or a bipartite one. Okay. Let me stop on time here. We're going to continue tomorrow with the result of why these moves are interesting. Thank you.